decided not to present what we are doing with respect to extending the semiconductor technology all the way to 5 nanometers or 3 nanometers. Didn't want to talk about 3D FinFETs, 3D memory devices, new materials with higher mobilities, transistor architectures that are very energy efficient. But what I thought is that I should look at Internet of Things from a semiconductor company and look at what are some of the challenges, fundamental challenges that need addressing. And I thought I'll share some of the ideas with you in that context. Other speakers certainly have talked to you about one of the most important issues with the IoT, that's the security and privacy. And other speakers have talked about network infrastructure and certainly talked about the economic impact of IoT in the markets. So I would specifically focus on the energy storage and energy harvesting technologies I believe are needed to make the vision of IoT a reality. So just a little commercial for Applied Materials for those of you who may not know. We were founded in 1967 in Silicon Valley, about a 45-year-old company. And the numbers are a little low. 2013 revenues about $7.5 billion, and market capitalization today about $24 billion. And 2013 R&D is about $1.3 billion. Going back to what Rakesh was saying, this is an extremely R&D intensive industry, and as we are looking at 10 nanometers, 14 nanometers, or even 28 nanometers, you're really looking at atomic control of matter. Everything that you're actually doing in the IC industry is tuning the properties of the surfaces and interfaces that really requires atomic control. We are across the globe in 18 countries, more than 80 locations. And Applied Materials actually is one of the first companies in China. In fact, they're the first wafer fab equipment company to have operations in China. We started that in 1984, and in 1994, we established our headquarters in Shanghai. And in 2006, we created a global R&D and procurement center. And you can see a very large footprint with respect to customers we have, research development and engineering locations and training locations in China, as well as sales and supply chain operations in China. So we are in China for more than 30 years, and we have about 1,000 employees. So now let me talk about our legacy and what we do and how is it a fit as we think about opportunities in IoT. Fundamental to what we do, we call it precision materials engineering. What that really means is atomic control of matter, and atomic control of matter is at the heart of enabling very large industries. So if you're looking at semiconductor industry, over the 40 years, the cost of transistor has come down by 100 million times. If you're looking at the display technology, the costs have come down by 20 times over the last 20 years. So cost to process a meter square of substrate has come down to less than $1,000 today, from $30,000 to $40,000 if you go back to 25 years ago. And if you look at solar PV specifically, and it's reaching grid parity in several parts of the world. And in fact, the cost per watt has come down about 6 times in the last 8 years. So continuous improvement in the technology, in a roadmap fashion industry, the entire ecosystem working, driving the cost down and creating very large industries is fundamentally what we do. So this is something I tell my son, high school students, if you had a smartphone in 1974, that would have been worth $10 billion. So what is PME? as I mentioned, PME is atomic control of materials, whether it is deposition, annealing, depositing metals, depositing dielectrics, planarizing them, etching them, inspection, metrology, implanting to change the properties, is essentially at the heart of what we do when we look at multiple industries. So how do we think about Internet of Things? And one way to look at this is that we are in an era of convergence. We are combining computing, mobility, user interface, and open platforms. And we are going towards the age of connectivity, and we could argue that we are in the first phase, connected consumer electronics, we're going to connected industries, and of course today's topic is connected everything, Internet of Things and Internet of Everything. So some of the technologies that are required, in addition to energy efficient transistors, memory that is inexpensive, low latency, doesn't require a whole lot of energy, but you also need a whole lot of new things. You need technologies for smart sensors. I think Rakesh called the semiconductor industry enablers. So you need to enable a whole lot of things like smart sensors. You need new materials for very efficient energy harvesting devices that are cheap. And I won't be talking about network architecture or big data analytics because others are talking about that. So, the question is that how big is the Internet of Things, and depending on which conference you have gone, you will come with a different opinion. Qualcomm said 25 billion by 2020. These are devices. Cisco talks about 50 billion by 2020. Intel talked about 200 billion devices by 2020. And these are all devices, and each device has at least state-of-the-art cell phones have anywhere from 8 to 10 sensors. So there is an organization called Trillion Sensor, and so these are sensors, not devices, and they're talking about somewhere around 60 to 70 trillion sensors by year 2032. So by any definition, it looks like a big market, a big growing market. So the question I'm asking is that what are some of the fundamentals, material science related problems, and how can a company like Applied Materials enable the IoT? So if you look at the near term, I'm sure the speaker from ARM is going to say more about it. There is going to be a threefold growth in the next 4 to 5 years by 2018 in wireless sensor networks. So while 2032 is great, while you might have an opportunity for 50 trillion sensors, but the growth is immediate, growth is near term, and it is happening as we speak. So one framework to think about IoT, especially as I begin to understand the challenges of energy storage and energy harvesting, is this framework. So node is essentially your device, whether it is one form or other of wearable devices, glasses, smartwatches, Fitbit, and things like that. And there was some discussion just a while ago about how nodes talk to a hub, whether it is a smartphone or a router, and a variety of protocols, a dozen or so ultra-low power communication protocols. Certainly standardization is required there. And cloud is where the action is going to be, presumably. You have storage on demand, processing and analytics, and certainly a whole lot of innovation is needed in the communication protocol with the hub and cloud. So if you look at the node, one challenge is the energy storage. In fact, if you do a teardown on some of these devices, they just happen to be batteries with some electronics around them. If there is a Moore's law for battery, there is doubling in the energy density somewhere from 20 to 30 years. So it certainly requires a paradigm shift in thinking about energy storage, because some of these technologies may not happen if you need to charge them every hour or every 2-3 hours. So that is a high value problem that I'm going to talk about. So The fundamentals of precision materials engineering are applicable here. So if you are looking at making sensors, coming up with new active materials, energy storage, or energy harvesting devices, you need certainly state-of-the-art technology platforms, whether it is the semiconductor 200 millimeter or 300 millimeter based platforms, large area technologies that we apply for display. If you take a Gen 8.5 tube, that's roughly 3 meter by 3 meter substrate, and you can put films with atomic control on that with 50 sheets per hour. So, truly nanotechnology and a very large scale. Roll-to-roll technology platforms, we have something called Smart Web, and it deposits aluminum with about 10 nanometers thickness. Get this, 70 kilometers an hour. So you need to have a variety of technologies that are going to be deployed, so you have the right cost point for right performance for the right sets of technology. So just a segmentation as I think about the energy storage needs for IoT, wearables, home automation, industrial automation, infrastructure. And what are some of the common things you need with respect to battery? You need thinness, you need a high energy density, especially if you're looking at wearables, and presumably a compliant structure. If you're looking at home automation, again, you need high cycle life. Low self-discharge is a big deal, whether it is batteries for home or batteries for Tesla or electric vehicles. High operating temperature is a requirement. Safety is a big deal. If you look at the battery technologies today, they're all based on lithium technology, they have electrolytes, they're flammable, and if you have thermal runaway, they can uncontrollably burn, and in fact that's a big issue. And so cycle life you require, calendar life you require, high operating temperature, very high energy density, and thinness are some of the common problems if you are looking at IoT. And presumably if you can come up with solutions for IoT and create a technology roadmap similar to Semiconductor Industry Association technology roadmap for semi, presumably this technology could be a solution for electric vehicles one day. So what I'm talking about are a class of new energy storage devices, new devices to the world, so to speak. These are solid-state batteries, and if anybody is interested, we published a story in MIT Technical Journal a month ago on solid-state batteries. And what solid-state batteries essentially do is address the diametrically opposing requirements of small form factor and long battery life if you're looking at wearables. So if you look at the current state-of-the-art lithium batteries, they run out of steam somewhere around 650 watt-hours per liter, and solid-state batteries can take you to double the energy density of that. Secondly, they are conformal form factor. They have a very long cycle life, so there's very low self-discharge. So by definition, these are solid state, so they don't have any liquids, they don't have any flammability, so you would not have any safety issues. So if you're actually looking at, let's say, a contact lens that would have a battery, this would be perfect for that, because you don't really want to put lithium battery in your eye. You don't want to have fire in your eye. So similarly, if you're looking at the industrial IoT, you need to have a very high operating temperature range. You need to have high energy density, low self-discharge rate, long shelf life, and long cycle life. So this is something that we're actually working on. We have a repeat customer. We are working with some of the customers. It's in the early stages. It's in the stages of creating this market. So in addition to that, you also need energy harvesting. For a trillion sensor vision to be a reality, energy harvesting has to go hand in hand with energy storage. So whether they could be PV-based or thermoelectric-based or piezo-based or other technologies. And again, this is a fairly large opportunity. And this is just one example of one of the startup companies is working on harvesting motion energy, piezoelectric vibration energy basically. And many of this, as the chair was talking about, milliwatt to microwatt, and in fact the cost is competitive for many of these energy storage technologies in that domain. Again, this requires new materials, it requires atomic control, it requires atomic engineering, something we do every day in semi, display, and solar industries. So in summary, this is a very large opportunity, whether it is 25 or 200 billion connected devices, trillions of sensors by 2026, tens of trillions of devices, tens of trillions of sensors by 2032. And I think we are in the very early phases, and we are in the first phase of connectivity, and certainly energy storage and energy harvesting need to be addressed. And of course, we work with customers every day in extending the semiconductor industry technology roadmap, and certainly work with our customers in display and coming up with energy efficient displays as well. But in addition to that, we also believe that some of these technologies need addressing for this vision to be a reality. And I fundamentally believe that if you can control matter with atomic control, you can solve problems in multiple disciplines. This just happens to be one of the new areas that we are actually looking at. Thank you.